All right, I think we are live. Hello, everyone. Good morning or good afternoon, wherever you are. Welcome to our Quantum Chaos seminars. Thank you for joining us today. As usual, I'll just remind everyone that the way our seminars work is that you'll be watching the stream in via YouTube, and we encourage you to interact with the speakers and with us through the live chat, asking questions throughout the talk if you want, and particularly in the Q&A session at the end. All right, so with that, I'll introduce today's speaker, which is Lennart Dabelow from Bielefeld University. Lennart is doing his PhD in the condensed matter theory group led by Peter Reimann, and his work and his interests include the study of thermalization and relaxation in closed many-body quantum systems, and particularly the effect of perturbations in those processes. And today he's going to tell us about typicality approach to perturbed quantum many-body relaxation. So we are really looking forward to your talk, Lennart. Thank you for joining us, and take it away when you want.
Yeah, thanks, Pablo, for the kind introduction, and thanks to you and Peter for giving me the opportunity to take part in this intriguing seminar series here. So, yeah, as said, this is joint work with my PhD supervisor, Peter Reimann, what I'm presenting here. And we're generally interested in questions of equilibration and thermalization in many-body quantum systems. And in this project in particular, we've been trying to find general principles for the relaxation of such systems. So the route from non-equilibrium to equilibrium. And quantum chaos, which is the title of the seminar series, it arises here as a tool or a paradigm, if you will, to treat a large number of systems simultaneously. So the overall motivation, or the general goal, the long-term goal, is to understand the behavior of macroscopic systems with many degrees of freedom based on the microscopic laws that describe their individual constituents. Or in more technical terms, you could say we want to derive statistical mechanics from quantum mechanics. Yeah, and I contend that we understand quite well why many-body systems eventually equilibrate, meaning that their dynamics becomes sort of stationary, and why they even thermalize, so that these stationary values can be described in terms of some traditional thermodynamic ensemble, like the microcanonical or canonical one. That is to say, there are concepts like the eigenstate thermalization hypothesis and typicality, as well as numerous numerical and experimental results, all of which show or demonstrate that this is sort of the generic behavior of such systems. So don't get me wrong here, I don't want to say that everything is satisfactorily understood. It's just that there is a large body of literature on these topics. And in comparison, we know only relatively little about how this relaxation actually occurs. And in particular, we have relatively little analytical principles. So this is precisely the focus of my talk here. To get the setup straight from the beginning, we're focusing on isolated many-body quantum systems, in particular on systems whose Hamiltonian can be split into two parts. So we have an unperturbed or reference system here with Hamiltonian H0, and then we add to this some perturbation described by this operator V here, whose strength is controlled by this parameter lambda. So the question we want to address in general is, assuming that we know how the unperturbed system behaves, can we say something about the dynamics of the perturbed system? And in case you're not yet well convinced that this could be interesting, here are three examples of situations that could possibly be covered by such an approach. For instance, you may think of the unperturbed system consisting of two isolated subsystems. And let's say for concreteness that we want to measure the energy difference between these two boxes here. So if they're completely separated, then whatever this energy difference is in the beginning, it will stay at that value for all times. And this is sort of sketched by this blue dashed line here. Whereas if we now bring them into contact by means of some interactions, perturbations, so that they can exchange energy, then the system will generically approach some new joint equilibrium state. meaning that the dynamics could look somewhat like this red curve here. Another interesting case is when the unperturbed system is integrable, because in that case, we may even be able to compute the dynamics exactly analytically. And what one often finds is that if we start from some non-equilibrium state, then there is some relaxation towards a stationary state, but this stationary state may not, or the expectation value in the state may not coincide with the thermal prediction. And it may instead be better described by some generalized Gibbs ensemble, for instance. Now, if we add to this an integrability breaking perturbation, then this commonly leads to what's known as pre-thermalization, where the system still follows the unperturbed behavior for quite some time. And especially it may spend some time close to this non-thermal equilibrium value of the unperturbed system, but eventually it takes off and departs towards the actual thermal value. And even more generally, you may think of just any isolated system for which you happen to know the dynamics, for instance, because it has been measured, and then you perform you change some parameter and then perform a quench. And then we could ask, can we say something about the dynamics of this new quenched Hamiltonian? And I should emphasize that the theory I'm going to present will not cover all scenarios that can be roughly fitted into these settings here. So these are just illustrations, and we'll encounter some additional assumptions along the way. So yeah, in particular, I'll say something about the applicability towards the end as well. But we can start collecting two key assumptions already, and this is, as should be evident from the title of the talk. The first one is that we're dealing with systems with many degrees of freedom, and you may really think of macroscopic systems with on the order of 10 to the 23rd particles here, even though the theory will turn out to work for systems with a few tens or hundreds degrees of freedom. This is really what we have in mind. So it's about the emergence of statistical mechanics from quantum mechanics. Second assumption is that the system is isolated, and this has some implications. Namely, it should have a well-defined energy from a macroscopic point of view, meaning that if we were to measure the energy, we want to get back a value from some well-defined energy range or interval, so that if you look at the many-body spectrum, your state should only populate some energy window that is macroscopically small with significant weight or with significant probability. But at the same time, this energy window will usually still be microscopically large, so it still contains an exponentially large number of levels in the degrees of freedom. And moreover, an important assumption is that the density of states within this window is roughly constant, or that the functions we're looking at are slowly varying so that you can approximate the density of states by a constant. And since this many-body spectrum is extremely dense, this is actually not a very restrictive assumption. It's quite generically fulfilled. Even more so because there is level repulsion in generic systems and these kind of things. Okay, so let's consider a little closer the objects we want to inspect. I said we have a Hamiltonian with an unperturbed part and a perturbation. Then there is a quantity we want to measure, which is given by some operator A here. And then the system is prepared in some initial state that can be pure or mixed. And we generally describe it by some density operator, rho of 0. And since the Hamiltonian is time independent, we can immediately write down the state at any later time, which is just given by the initial state, rho of 0, propagated with e to the negative IHT. And the expectation values of the observable are then given by the trace of this time evolved state times A. Then we can do the same thing for the unperturbed system, of course, where we start out from the same initial state, rho of 0, but now propagated with the unperturbed Hamiltonian H naught. And then in formal terms, the question we want to answer here or address is, can we say something about the time-dependent expectation values of the perturbed system given the unperturbed dynamics here? All right. So in complete generality, there's probably not much more you can say about that than what's given on this slide. So to make any progress, it's clear we'll have to make some sort of assumptions. And What comes in handy here is the large number of degrees of freedom. So this is what we want to exploit. And I think we all agree that it's a phenomenological fact that the behavior of macroscopic objects is sort of insensitive to the microscopic details. So to describe a macroscopic object, I don't have to know what every individual atom in my object does. For instance, if I take a ball now and I throw it out of the window here, it may be sufficient to specify a position and velocity and perhaps some rotational degrees of freedom and friction. And that will give me a pretty good description of the process without knowing what all the atoms do. So let's say on the order of 10 variables are sufficient to describe the system as opposed to 10 to the 23rd. And the same, of course, applies to the traditional thermodynamic systems where you look at your coffee cooling down or ice cream melting or anything. So this is what we want to exploit. There is this insensitivity to microscopic details, and hence the idea that that the approach here, this typicality approach, entails is that instead of one particular perturbation that we're interested in, we temporarily look at an entire class of very similar perturbations or an ensemble of perturbations, which means that this operator V, or more precisely its matrix elements in the eigenbasis of the unperturbed Hamiltonian, they become random variables. But crucially, the distribution of these random variables should emulate the essential characteristics of the true perturbation as closely as possible. So in particular, what you often find in such systems is some sparsity, meaning that most of the matrix elements are zero, or some banded structure where the magnitude decays with the energy separation of the coupled levels. And this should ideally be built into the model to keep these characteristics. So for instance, sparsity and bandedness arise if you have a non-interacting unperturbed system, then you add some interactions by means of this perturbation, which are local and few-body, for instance. Okay, well, these are still rather abstract properties. So let's, oh no, first I want to, okay, so given this ensemble, let's see how we can make use of it. And the idea is then that instead of looking at one particular realization, we look at the average behavior or the average effect of all perturbations in our ensemble. And surprisingly, this is something you can evaluate, even though it is really hard to say something about an individual perturbation or any given perturbation. But in order for this to actually be useful, in a second step, we want to look at the deviations for one particular realization from the average behavior. And the goal here is to establish that these deviations are very small. So we look at the variance of these fluctuations, and it will turn out that these fluctuations are exponentially suppressed in the degrees of freedom, which means that in a sufficiently large system, practically all perturbations in the ensemble cannot be distinguished from the average behavior, meaning that this average that we computed in the first step actually becomes a prediction for an individual realization here. Okay, so that if you've done that, you still want to show that, or you want to argue that the true perturbation that you were interested in originally is one of these typical members. And to do so, it is of course crucial that your perturbation ensemble implements the key characteristics, as I mentioned before. Okay, so here's the ensemble we're using. It's basically defined by just 3 properties. And the first property, which is certainly the most restrictive one, is that all the matrix elements are independent except for some hermeticity constraint. So this will clearly be violated in a true system because, I mean, there are some correlations that arise due to the geometry of the problem or whatever. But the decisive point here is that these correlations should not be the essential mechanism behind the observed behavior, and even more, you can relax these conditions somehow, so mild correlations may still be acceptable. I'll say something more about it later as well, but for now we just keep it as an assumption or a prerequisite to continue. The second property here is not very restrictive at all. It means that the the mean of these matrix elements should be 0. So for the off-diagonal elements, this essentially amounts to an unbiasedness in your choice of phase factors for the bases you're using. And for the off-diagonal elements, it's merely a shift of the energy scale. So that's a sort of trivial assumption, you could say. And the important characteristic and the connection to the true perturbation is given by this second moment here, which I will also call the perturbation profile. And the assumption is that we can write the second moment as a function of the energy difference of the coupled levels. So you see that this immediately implements a banded structure. If this function happens to decay for a large argument, then you get some band profile of the perturbation. And the idea here is that the true matrix, for the true matrix to extract this perturbation profile, you want to sort of locally average over levels that are close by in energy here to see what this function looks like. And similarly, you can implement sparsity, for instance, by adding some delta distribution in your probability distribution for these matrix elements. But it will turn out that all these further details beyond these first two moments are, technically of subleading importance. There is some sort of central limit theorem acting. So the really decisive characteristics are just these first two moments here that we need. And I want to introduce at that point two parameters associated with this perturbation profile here, which is the sort of the intrinsic energy scale of the perturbation. This is just the magnitude of the levels in the vicinity of the diagonal. And then the energy range or the bandwidth of the perturbation, you could say. So this can be infinite if the perturbation doesn't have a band structure, but in general, it may be some finite number that quantifies the extent to which energy levels are coupled by the perturbation. All right, this has all been very abstract. Let's look at a concrete example here. And that's a two-dimensional spin 1/2 model where we're coupling nearest neighbors by Heisenberg terms in the unperturbed system. And this is sketched by these solid links here. So we look at a 4x4 lattice. And then for the perturbation, we add some spin flip terms between next nearest neighbors as sketched by these dashed links. And for this 4x4, so 16 spin lattice, we can diagonalize the system exactly, numerically. And what we obtain is such a structure here. And let's focus on the left panel first, where you see an average. So every pixel here corresponds to an average over 100 by 100 matrix elements from the middle of the spectrum here. And yeah, you nicely see the banded structure already, as indicated by the color gradient. Yeah, and now let's look at a close-up of the central segment here, where every pixel is now an individual matrix element, and then you see that the matrix is also sparse because most of the space here is white, so there are these matrix elements are 0 or almost 0. So this second feature is also recovered. And the perturbation profile that I introduced on the previous slide is sketched here, the empirical one. So here we're plotting the magnitude squared of the matrix elements against the energy difference of their levels. And you see it is a sort of smooth function. And yeah, particularly it can be fitted by some exponential form here. So we can make an ansatz of this form where we have a prefactor sigma squared and then an exponential that decays with some bandwidth delta V here. And we find for the parameters, sigma squared is 0.005 and delta V is 7.3. You get this red line here. And it reasonably describes the decay reasonably well, I would say. And to illustrate to you how to embed such a true perturbation into a particular random matrix ensemble, I now generate a random matrix which has the same sparsity as the one that I can extract from here. And for the non-vanishing entries, I just use some normal distribution with the same variance as found here. And then we get a picture like this, which on the coarse-grained level looks pretty close to the empirical or true perturbation here. Whereas in the close-up, you do see some differences. So the distributions don't agree perfectly, and it looks like the true perturbation is not really Gaussian. But as I said before, it will turn out that this is essentially not important if the system is sufficiently large. So then we only need, it's only important that the second moments agree, and that they do by construction. Yeah, and you also see here that, of course, the random matrix model is is sort of smoother in its dependence on the, or the properties are implemented more smoothly, yeah, by construction essentially. Okay, so that was just an example. I can assure you that there is much more evidence that these banded and sparsity, banded structure and sparsity are found very generally. So there are semi-classical arguments to support it. There are analytical results for some types of lattice systems, and there is a large number of numerical examples that you could look at, which all find such properties. Okay. Yeah.
Just a quick question. In the results that you're showing there, which the ones that correspond to the actual Hamiltonian on the top, did you say that there was some averaging going on?
In this panel here, you mean? In the, or in
yes,
the,
in some. I thought I heard that, for example, on the plot on the left, there was
the plot on
you
the
were
left,
averaging.
In the plot on the left, every pixel that is shown here is an average over 100 by 100 matrix elements, basically, because the scale is. And of course, here is some averaging involved as well on the right. So that there's a binning. I think it corresponds to roughly 5 level spacings, mean level spacings that is used.
Got it. Okay, but the H0 and B are always are kind of deterministic matrices. They are not random.
That's a single example. There are no random coefficients in the setup here.
Thank you.
Okay. Yeah, let's move on. So I said we want to compute the perturbed expectation values, or we want to predict the perturbed expectation values. So if we write them down in the eigenbasis of the perturbed Hamiltonian, we find something that looks like this. So these are the energy levels of this perturbed Hamiltonian, and here we have the matrix elements. And even though the initial state and the observable are fixed, so independent of the perturbation, of course, if we express everything in the perturbed Hamiltonian basis, then these will be random as well, and that's a little inconvenient. So would be nicer to separate this this randomness, and this can be done by transforming to the unperturbed basis by means of these transformation matrices here, so the overlaps between the perturbed and unperturbed eigenvectors. And in this expression here now, the matrix elements of the initial state and the observable in the unperturbed basis, they are fixed, and the only random quantities is the prefactor here, involving these 4 factors of overlap matrices and the energy levels. But regarding the energy levels, I want to make one more assumption, that is that we can approximate this energy difference here in the exponent by its mean over the ensemble. And this is an approximation which is actually very well controlled, so you can check afterwards that the error you're making here only kicks in at times way beyond the relaxation time that will be found. So that's a safe thing to do here. Okay, so the only random quantities remaining here are these 4 factors of overlap matrices, and consequently this is the key element that we want to look at. Oh yeah, and I denote the, I should have said that before, I denote these averages by these brackets sub V. It occurred already on a previous slide, I guess. All right, and if you want to compute the variance, then of course you need 8 of these factors because you need the square of this expression as well. And it turns out that an important role in the entire calculation, we'll see that later as well, is played by the second moment here. Which is closely related to the local density of states. It is essentially the average, the ensemble average of the local density of states, which may be familiar to some of you in the quantum chaos community. But yeah, physically what this quantity tells us is how much you could say the unperturbed eigenvectors contribute to any perturbed eigenvector. So if we expand a perturbed eigenvector in the unperturbed eigenbasis, then the expansion coefficients are precisely these matrix elements here. And if you take their absolute value squared, it tells you the weight of the muth eigenvector in the nth, of the muth unperturbed eigenvector in the nth perturbed eigenvector. Okay, so from a mathematical point of view, the important quantities we want to investigate are the averages over such factors of overlap matrices, and we'll do so by exploiting what's known as supersymmetry methods, where you use a combination of commuting and anti-commuting numbers, and I'll say a little more about it on the next slide, to express these overlaps. I just want to briefly say that there are other approximation schemes for certain special choices of the perturbation. So, for instance, Charlie Nation gave a talk in this very seminar series here, where he introduced a method that can be used to compute these overlap moments for the Gaussian orthogonal ensemble. I looked it up. I think it was season 1, episode 4. So there you can see another approach. Then there is work by ETA and Ashcroft. They use some Lippmann-Schwinger type equations to perform a similar calculation for the Gaussian unitary ensemble. And actually, some time ago, Genway, Ho, and Lee devised a method based on Dyson-Brownian motion to also compute such overlaps. But okay, here we want to use these supersymmetry techniques, and the crucial idea, this will perhaps be the most technical slide of the talk, but it'll be over brief, I promise. So the essential object here is the resolvent, or the crucial observation is that there is this object, the resolvent, or the Green's function, which is defined as the inverse of this operator z minus h. And this resolvent encodes all the information we're interested in. So you readily see that the poles of this expression are precisely the eigenvalues of your Hamiltonian. And then the matrix elements, or the matrix elements here, they encode the overlap factors from the previous slide that we're interested in. So for instance, the second moment you can express like this as a linear combination of some matrix element and its complex conjugate. And for higher order moments, you can essentially compose them from such products as well. And the nice thing about these matrix elements here is that you can write them as a Gaussian integral. So let's focus on this part here first. You see in the exponent the inverse of the resolvent, which is just the matrix z minus h, and that's nice to deal with, let's say. And if you compute this Gaussian integral, then you get precisely the inverse matrix element evaluated at mu and mu. But there is some prefactor here, which is the determinant of z minus h. And this is a little nasty because this is pretty hard to compute, such a determinant for a high dimensional matrix, let alone its average, when what we're interested in eventually. So this is where this supersymmetry method comes into play, where the idea is that you can express this determinant as a Gaussian integral of a very similar structure as the commuting integral here, but now over so-called anti-commuting or Grassmann numbers, chi. So it's, for now, it's just a claim, let's say, that this Gaussian integral evaluates to this determinant. So if you combine the two expressions, you actually get an expression that is sort of symmetric because it has the same shape here. And it also gets rid of this this annoying prefactor for the matrix element. And then the next steps is that you average over the perturbations here. This can be done due to this central limit theorem like argument that I mentioned before, which means that this is essentially a Gaussian integral in the perturbation as well. And the effect is that now your integral over x and chi is of quartic order in the exponent. So you want to reduce that back to second order to have another Gaussian integral that you can deal with. And to this end, you perform some Hubbard-Stratonovich transformation, which has precisely that effect, that you can then integrate over these x and chi variables, perform the integrals that are written here. And then in the last step, you want to get rid of these auxiliary variables that you introduced during the Hubbard-Stratonovich step. And the way to do that is to use a saddle point approximation, where we exploit the large dimension of the underlying Hilbert space, so the large number of variables that we have here. Okay, so well, that's certainly technically a little complicated, but eventually what we find is the following expression, and let me walk you through the individual terms. So this is the ensemble averaged dynamics, and we have first of all, the long time limit here, this is the value that's approached as t becomes very large. And there is an explicit expression that we have for it, but for the most part, it is equivalent to the thermal expectation value. So under quite general assumptions, you can take this equal to the thermal expectation value. Yeah, then there is the unperturbed dynamics here, which is good because, of course, we were interested in relating the perturbed to the unperturbed dynamics. So this is what's happening right here. And then the deviations of the perturbed behavior from the unperturbed dynamics is encoded in this, what I will call the response profile, this function g of t here. And g of t is defined as the Fourier transform of the second moment of eigenvector overlaps, or the average local density of states, if you like. So this is one representation, and perhaps even nicer representation is by means of this integral equation down here, which looks very similar to familiar response equations, but the crucial or the important property here is that it is nonlinear in G. And it connects this response profile to the second moment of the perturbation matrix element. So the defining characteristic of our perturbation ensemble, you could say, because this V2 hat function here is the Fourier transform of this second moment. Okay. Then there is a rest term here, which turns out to vanish for small t, it vanishes for large t, and actually it vanishes almost, or it is negligible almost always, so it vanishes identically if the diagonal elements of the state and the observable are uncorrelated, which is the case, for instance, if the eigenstate normalization hypothesis holds. And even more generally, you can give bounds that entail that it is essentially negligible for all physically relevant cases, so that we can throw it away, essentially. Okay, so this was the first step of the proposed recipe. In the second step, I said we want to look at the variance here, or at the deviations for one realization from the average. And that's what I'm writing down here. And we find that this variance can be bounded by the operator norm squared of the observable times a number that is exponentially small in the degrees of freedom here. So if you remember that f is on the order of 10 to the 23rd, this thing here is an unimaginably small number, which means that in essence, we won't be able, if we draw a perturbation randomly according to the distribution, we won't be able to distinguish the observed behavior from the average. And that is what I'm writing here now, so that the vast majority of individual perturbations show the average behavior. And this is, this is our prediction for the dynamics, you could say, and this is how it arises. And of course, the main ingredient in this prediction is this function g of t, which satisfies this nonlinear integral equation down here. All right. So in the first step, I wanna look a little closer into this function g of t to see what properties it has. So I already told you that in general it solves this integral equation, this is actually quite, I mean, you can straightforwardly integrate it by standard techniques. Essentially, a forward Euler integration will give you a decent result here for largely arbitrary perturbation profiles. So that's already, it's already easily dealt with, let's say. But we can even say some more, or get some more analytical expressions in certain limits. For instance, we find that for small perturbations or at late times, g of t describes an exponential decay, where the decay rate is given by 2 pi times the perturbation strength squared divided by the mean level spacing, or times the density of states, you could say. And this is universally found again, regardless of the underlying perturbation profile. So if the coupling is sufficiently small or the time is sufficiently large, then you'll find this exponential decay. And it contains in particular some special cases that have been known before. So for instance, for perturbations from the Gaussian orthogonal ensemble, you also find this exponential decay. And it also entails Fermi's golden rule as a special case. And in particular, the prediction is that Fermi's golden rule always applies at late times here. Even though, well, there is nothing said yet about how late these times are. And the opposite limit of very large lambda or of very small times, you find that this response profile is given by this expression here, which involves a Bessel function of the first kind, and then divided by its argument. And the inverse time scale here involves now, again, the perturbation strength, and then also the bandwidth that I introduced earlier, so the energy range of the perturbation. And this expression might be familiar to you as the fidelity in random matrix models or under Hamiltonian evolution from the Gaussian orthogonal or Gaussian unitary ensemble.
There's a quick question in the chat.
Yes.
So how is G of t related to the spectral form factor? Are they the same in some particular cases?
The spectral form factor, you have to remind me what that was. I think the initial state times the Fourier transform of the initial state or something.
Yeah. With if you take the fidelity, I think Pablo is joining.
I was interpreting it as the Fourier transform of the density of states, right? Or
of the density of states. Yeah, then you could see this as a limiting case. I mean, if the perturbation becomes very large, then the perturbation dominates the spectrum, let's say, and then the local density of states essentially becomes the density of states of the perturbation, and then you might see this as the limiting distribution here. But in general, G of t is the Fourier transform of the local density of states, so the density of states weighted by the eigenvector overlaps between the perturbed and unperturbed systems. Hope that answered the question. Otherwise,
thanks.
Thank you.
Okay, so we have these two regimes: weak perturbations, strong perturbations, or small times, large times, and in between there is a crossover between these two regimes. And I mean, the details don't matter that much, but we can quantify where this crossover is supposed to happen in the coupling strength and in the time. So it essentially tells you where the transition from weak to strong perturbations, for instance, occurs. Right. So this is already nice. I mean, these are some analytic approximations, but it turns out that we can actually go one step further and even obtain some sort of second order approximation in some sense. And that is again an entirely analytic approximation. It's given by this expression here, where the details are not that important. Perhaps we can say that it's a linear combination of three exponential functions here with some rates, and these rates are determined by just two parameters of the perturbation. And one of them, these are essentially the two parameters that I introduced in the beginning. One of them quantifies the overall energy range or the perturbation strength, the magnitude of the matrix elements near the diagonal, and the other one quantifies the bandwidth of the perturbation. Okay, so that's already an interesting result, let's say, because I mean the distributions or the possible perturbation ensembles, they were very diverse, but it turns out that in the end you can describe or seemingly describe the dynamics well by just two parameters. And that's something, of course, I want to show you, illustrate to you. So let's come back to our example from the beginning first, where remember we had this 4x4 spin lattice with this Hamiltonian here, and it led to this sort of perturbation profile here, for which we obtained the particular values of 0.005 for the perturbation strength and 7.3 for the bandwidth. Yeah, and now we just pick some observable, which is the magnetization correlation between two spins from the center of the lattice. And then an initial state, which is based on some random or infinite temperature state phi, but then we deflect these two states, these two spins that we're observing in order to have some non-equilibrium conditions. And we then also apply some Gaussian filter here, essentially to satisfy the constraint that we have a well-defined energy shell. So you could think of this as a macroscopic measurement of energy, which sort of narrows your state down to an energy window. And for this setup, you can also evaluate the thermal value simply by substituting. I mean, we have all the information from exact diagonalization, so we can just compute the thermal value and find that it is negative 0.08 here. Okay, so for this special combination of observable and initial state, here is the dynamics that we find. First numerically, so this is again the exact result for this model, you could say. And we have the unperturbed dynamics in black here, with the dashed dotted lines, whatever, and the perturbed dynamics now for various values of lambda, they are given by these dashed lines. Okay, so now we can go ahead and use our prediction from the previous slide. So the second order approximation for the function g. As I said, we know these parameters sigma and delta exactly, so we can compute this prediction exactly. And what we find are the solid lines here. And I think they agree pretty well with the numerics here. So it looks like the theory really predicts the behavior of this system correctly, you could say. Oh yeah, and just to demonstrate, so the lambda values I'm choosing here, they actually cover the entire transition from weak to stronger perturbation. So the crossover coupling is at 0.75, I think, in this ensemble, and the so in between the green and the blue curve, and the crossover time is at about 0.4. So here, you could say. And just to illustrate to you, I'm also plotting now the weak perturbation or late time approximation, this exponential that we had, and you really see that these are the dotted curves. I hope they're visible on screen. You see that indeed it works for small lambda, and for late times it fits the data quite well as well, but there are noticeable deviations for small times and large values of lambda. So this is where the band structure actually becomes important of the perturbation. Okay, so this is one example. Perhaps we might want to look at the second example here, which is I just want to emphasize that there are no free parameters here. So there's nothing fitted or anything. Everything is known exactly from the underlying exact diagonalization of the model. And that will be a little different in the second example here. That's why I'm emphasizing it. So this is the bosonic Hubbard model. So it has some hopping terms here between nearest neighbors, and then some repulsion between nearest neighbors as well. On-site repulsion, I'm sorry. And yeah, so for the unperturbed dynamics, or let's say this system was studied numerically in Eisert's group in Berlin, and using their data now to compare the theory. And for the data available, it turns out that it is convenient to take the U to infinity limit, so the hardcore boson limit, you could say, as the unperturbed Hamiltonian, and then there is an expansion in the inverse coupling strength here, and this becomes our perturbation parameter, and the perturbation is sort of the first order correction here. But in the unperturbed case, so for hardcore bosons, with the initial state being one particle at every other side, so let's say even sides are occupied, odd sides are unoccupied, and then we're observing the single side occupation of an odd side here and some hopping correlation. And the unperturbed dynamics, which is these black lines here, they can be obtained exactly analytically. And then in this paper here, they performed a numerical study for finite values of U, which I translate into values of lambda, and they yield these colored dashed curves here, which are shifted by some offset 0.25, I guess, to make them better visible. Okay, so now we can try again to describe this by the theory, but here the problem is that we don't know the perturbation profile. It's just not given in this publication. I think the numerics is done for some 30 or 35 particles, so that may very well be beyond exact diagonalization possibilities as well. So we have to resort to fitting. But importantly, there is only one parameter that I'm using to fit here. So I'll show you the fit first. These are the colored lines here that we obtain. And I'm using now the weak perturbation approximation because it turns out that all these values of lambda, they are still in the regime of moderately weak perturbations. And the advantage of this is that I only need one fit parameter instead of two. So if I wanted to use the other approximation, I needed to fit both this proportionality constant here and the bandwidth. Okay, so again, these are two different observables, and I don't know, 5 different dynamics for different perturbation strength, different systems, and a single parameter is sufficient to describe it completely. Oh yeah, and then there is actually an experiment performed in the Bloch group, I think, where they tried to emulate this system in a cold atom setup. And here's a comparison of their experimental data, which are the dots here, to the theory again, where we find pretty good agreement, especially for larger values, again, of lambda. And that, yeah, it's the same same fit parameter as here before. So there is no additional fitting between these plots and these. They all use the same parameter of this proportionality constant. Okay, so I guess I've told you enough about how brilliant everything works. So let's look at the cases where it actually fails or where it could fail. And that's a little, I mean, it is inherent to this typicality approach that the entire argument is probabilistic, meaning that our statements are always only for the majority of some given ensemble. And in principle, there can always be exceptions or atypical setups. And it's hard to tell what these atypical setups will be a priori. The only thing we know is that the fraction of atypical setups will decay exponentially with the degrees of freedom. So that you might expect that it should apply in general, unless there are specific reasons to the contrary. And what could such specific reasons be? Well, could be that we're not capturing all the relevant characteristic with our perturbation ensemble. So here, the defining property was this perturbation profile, the second moment of the perturbation moments. But it could be that there are other important features of physical perturbations that play a role. So, for instance, these could be conservation laws of the perturbation, which are not conservation laws of the unperturbed Hamiltonian, and then most of the random perturbations in the ensemble will violate these conservation laws. But crucially, the other way around still works. So if H naught has some conservation laws that are then broken by the perturbation, that should be fine, because like the true perturbation, the majority of perturbations in the ensemble, they also break these conservation laws. A perhaps more important aspect could be the fact that interactions in physical systems are typically local and few-body. And you see this, for instance, by looking at, let's say, an example that has some macroscopic spatial inhomogeneities. So the prediction here said that all observables essentially behave the same way and they relax on the same time scale. But obviously that cannot be true if you say you have a local perturbation that acts on a very limited region of space, and then you have one observable that sits close to this region, or it probes the vicinity of this region. Then this observable will notice the perturbation earlier than an observable that sits far away from it. So I mean, there are rigorous bounds like Lieb-Robinson type, etc., that tell you that these two observables have to relax on different time scales. So such situations can obviously not be described by this approach. And so these features should then be included, of course. Yeah, so for instance, the situation that we have to exclude are our macroscopic transport scenarios then. But still, I guess I gave you 2 examples, and there are a variety of further examples that show that it still applies to a large variety of different models. So fermions, boson spins, different observables, different initial states. Yeah, that can be described this way. All right. Yeah, so to sum up, I hope I could convince you that we can sort of predict the relaxation under the influence of weak to moderate perturbations if we know the reference system, so some unperturbed system that is subsequently perturbed. And for typical perturbations from any of the described ensembles, we can actually predict this sort of analytically. Yeah, then and the resemblance between these unperturbed and perturbed dynamics is given by this, or the deviations are described by this response profile function g of t, which in turn is related to the perturbation profile by a Fourier the Fourier transformation of the perturbation profile by some nonlinear integral equation. And especially we have an analytical prediction that only depends on two parameters, namely the perturbation strength and the bandwidth, to describe this function g of t and to solve the integral equation. And yeah, it turns out that many physical systems actually show this predicted typical behavior. So that's it. Thank you very much for listening, and I'm happy to take questions.
Thank you very much, Lennart, for this really interesting seminar. So please, everyone, if you have any questions, post them in the chat and we'll put them to Lennart. So I think there's already one question. Can you elaborate on why this will fail when there is transport? Do you expect the approach to hold after the currents disappear?
Yeah, so the initial idea, I guess, I don't know when the question was posted. So the idea is that if the perturbation only acts locally, and then it is, this information has to spread through the system. So if there are local interactions and a local perturbations, then it takes some time until all particles take note of the perturbation. And if you're looking at a region that is far away from the perturbation, then it will take longer that it learns about it than in the region close by. And this is obviously accompanied by some macroscopic transport. So there is some current that is initiated at the location of the perturbation, then it spreads as time evolves. So if the currents have vanished, then it could very well be that the theory is applicable, but I'm also thinking that you won't probably see much because if the current has vanished, then the system will probably have relaxed completely already. So you will be more or less in equilibrium unless there is some other time scale involved in these local processes. But so generally speaking, it will probably be applicable, but it will not be very powerful or not very predictive in this case, because yeah, the prediction will be trivial because it says, well, you're in equilibrium.
Okay, thanks a lot. There's also people thanking you in the chat, and actually also have a question myself. So you make some assumption on these matrix elements of V, this randomness, this typicality. This all seems very similar to assumptions that are encoded in the eigenstate normalization hypothesis, where if your V is some local observable, you could basically use the arguments from ETH to claim that, okay, you have this randomness there. Can you briefly elaborate on the similarities and the differences between assumptions you make here and these?
Yeah, I mean, there are certainly some similarities. So well, let's see. It will take a long time to go back to that slide, but this was the basic structure.
Yes, exactly.
So you could, I mean, if you take the ETH and you focus on a narrow energy window, then this is essentially it, you could say. It just says that the matrix elements, because you have this term that depends on the average energy, but this is just equal to the energy in your window. And then you have the energy separation. But I think the assumption here is much weaker because, first of all, we don't need that the fluctuations decay with the system size. So we don't need, even though you might expect this generically, but they don't have to be suppressed in the number of degrees of freedom. And more importantly, the unperturbed system does not have to satisfy the ETH for this to hold. So I mean, it can still be, you can still take an integrable system and have this structure without needing, because this is only, you could say it's only a local average that you're performing. It doesn't mean that all the matrix elements have to obey this dependence here. It's only that when you take local averages in a small region around these matrix elements M and N, or if you could say you plot all these magnitudes against their energy separation, and then you perform a binning an average within these bins. So yeah, we don't need, I mean, the unperturbed system doesn't need to be non-integrable. So the ETH is not necessarily satisfied, but it should still somehow work. And there are examples, actually most of the examples that I know that we used have some special form of the unperturbed Hamiltonian, because in that case, you really see a difference by the perturbation. It really introduces a new time scale that is manifestly faster than the unperturbed dynamics. So that often in these examples, the unperturbed system is integrable and then therefore not expected to satisfy the ETH, or at least the strong ETH that is. Weak ETH may of course still be satisfied.
All right. I think Peter's internet is freezing, but I actually had a question. So I want to get your thoughts on something. I mean, by the end, you were showing results about basically a quantum simulation of the Bose-Hubbard model, right? It's a kind of famous experiment. So, you know, in your work, you're one way to look at it is that you're showing that you can predict how the expectation value is going to evolve in this particular Hamiltonian when you add, say, some interaction term or perturbation. And you can do that given that you knew the solution to some perhaps easier problem, right? H naught. And so given that, you know, these quantum simulations are basically trying to do things that in terms of dynamics, right? They are trying to access dynamics of observables that are supposed to be impossible to obtain, you know, with a classical device. Do you have any thoughts about how your work might push the boundary of, you know, what we thought that this expectation value was going to be just impossible to track because the system size is too big and the system is non-integral, so I cannot solve it. But actually, if I solve a related problem which is close by, which I can solve, and I apply some of these ideas, I can perhaps do some kind of prediction. Do you have any thoughts about that?
So, I mean, of course, ideally, you would hope that it works that way. So you have some analytically, let's say, or easily accessible numerical reference case that you can solve, and then you take the theory and you can predict a large number of different models or parameters. So the first caveat is that, of course, as I said, with this typicality approach, you can never be sure that the particular model you're looking at is amenable to the approach or to the type of ensembles you're using here. So I guess it is perhaps better to look at it from a foundational point of view and say that it explains a lot of the behavior we observe, even though we cannot possibly ensure that it will work in a particular setup. And another problem, of course, is that you still need some information about the perturbation. You cannot just take any generic operator. I narrowed it down here to just 2 numbers, but these numbers we would still need. So in complete generality, it'll be hard, but it can, of course, make it much easier to perform prediction, or you could at least get a first guess about the expected dynamics, and then see if this shows the phenomenology you're interested in, or if it is worth considering additional numerical or experimental efforts to pursue it. I don't know.
Yeah, that sounds very reasonable. Thank you.
Okay, so my internet briefly dropped out, but unless I missed anything, I think that concludes this week's seminar. So thanks a lot, Lennart, for giving this talk. Thanks a lot to everyone who's watching. Next week, we'll be back with Daniel Renner from Stanford University, and he will be talking about bounding the spread of quantum information and emergent classicality in dynamics of large systems. So for everyone who wants to get updates on upcoming seminars, you can just subscribe to the mailing list or subscribe to this channel in the